Welcome to the E-Padashala, the lecture series for the PG program in computer science. I am Rajeshwari Sridhar and I am going to talk about compiler design course, where we have divided this course into 40 modules. Today we will talk about the first module and which will be an introduction to compiler course. The main objectives of this particular module are to understand the processes involved in compiler design. And to start with, we will talk about what is a translator, what is a compiler, what is its need, etc. And we will also try to group them into phases of the compiler. So, let us go back to some history. So, where we can define software as an essential component of the current scenario. And normally earlier software was written in assembly languages. That is, you have a mnemonic pseudocode of instructions where the instructions were closer to the machine than to the human being. So, it was easier for the machine to convert and understand them in a better way, but on the other hand it was very difficult for the programmer to code instructions. So, therefore, what we tried to do was basically try to get some coding where we would try to program in a language which is closer to human beings, and on the other hand have some kind of a mediator who is going to convert this high level language into a low level language which the machine can basically understand. This is similar to you having a translator where you cannot communicate with another person who does not know your language. So, let us take for example, I am going to talk with a German. So, and I do not know German and he does not know English nor my local language. In that case, I will have a translator who could understand my local language and convert it into German and then give it to the other person for processing. So, this is what exactly the compiler basically does. So, we are in a position to need where we need a software that will understand human language. So, basically what we define is they are called as language processors, where we talked about an example as a translator. A translator is one language processor which essentially converts a source program into an object or otherwise called as a target program. Source program is what we call as a program written in one particular language, and we call something as an object program where it belongs to an object language. An object language in our context is going to be the machine language, that is, it is closer to the machine where the machine can basically understand it better. And we are going to have some examples of translators are your assembler, your compiler, your interpreter, etc. So, in the example which I gave you just now, where I am going to have a translator who is going to convert my language into a German language. So, this person is acting like a translator. Okay. So, what is its input? His input is my local language, that is, I talk to him, and then he gets that input, he interprets it, he understands it. So, he is not going to do a literal word by word translation, he could do that also, rather he could also convey an essence of what I have basically spoken. So, these are called as language processors. So, what you can basically try doing for our example is you can design an interpreter or a translator that converts human language to machine language. But what is the difficulty here? You have to parse and you have to get rid of ambiguity here. So, interpreting could basically be ambiguous. So, on the other hand, supposing say for example, the example which I gave you, a translator sitting in between me and a German speaking person. So, in that case if I try to mix up another language which the interpreter also does not understand, then it becomes a problem for him to translate to German. So, therefore, what he does is I have to give him input which he can understand and convert it to a German language. So, that is what we are trying to look at it here. So, what we do is we design a compiler that will understand high level, that is, it need not be a pure English language, but it is somewhat closer to English language where the humans are comfortable in coding, and then it is going to convert that to assembly language which the machine can basically understand. This is basically simpler, but it needs a mapping of the high level language to assembly language. So, and then what we can do is we can design an assembler that is going to convert assembly language to machine language. For example, here in the real life scenario, supposing if I am going to use, I am going to mix two languages where I will speak one sentence in one language, the next sentence in another language, etc. I could have a sequence of interpreters, sequence of translators who could get my language to language X, language X to language Y, and language Y could be converted to German by another translator. So, this is what we are trying to do it in the compiler scenario also, where the humans write in a language which is closer to English. Okay. This is called as a high level programming language, and I have a compiler which is going to convert this language into what is called as an assembly level language. The assembly level language is closer to machine language, and then this assembler will take this assembly language as input and convert this into machine language, which is going to be consisting of ones and zeros. So, what is the prerequisite here is the target language need to be specified, and the output of the various compilers are to be known prior time. So, this is a sequence of processing that could happen. You have a high level language which goes through a software system called as preprocessor. The preprocessor basically tries, it's something like a fill up the blanks. So, where it is trying to, you have what is called as a macros. You normally have a hash define, you have what is called as a macro which is written in your hash include, your hash define, all these things. All these things will be unstripped and you will convert that into a complete source program, and then the source program will be given to the compiler. The compiler will convert this into a target assembly language program. What it should basically get as input is the instruction set should be given to the compiler for generating assembly instructions, and then the assembler will basically take this input and convert this into a relocatable machine code, which is going to consist of ones and zeros, and finally the linker will link several modules into a single thing and then loads into the main memory for execution. That is done by the loader. So, here let us look at some history of the compiler, where the first real compiler was built for Fortran in the late 50s, and it required 18 years to build. So, what we are trying to look at as a definition of the compiler is, it is going to definitely act as a translator, transforming human oriented programming languages into computer oriented machine languages. It does not care about the machine dependency. Okay, that is not required by, the machine dependent details are not required by the programmer. It is up to the compiler to know what is the target machine for it to translate this high level language into assembly language. So, in the process of generating assembly language code, the compiler can basically try to generate a pure machine code or an augmented machine code. A pure machine code basically has an instruction set. It basically assumes, without assuming the existence of an operating system or library, it just has an instruction set, okay, without no knowledge about the operating system or any library available, and it is basically having a it's basically used for operating systems or embedded applications basically. And the augmented machine code is what we are interested. It is code with the operating system routines and runtime support routines. So, that is what we are trying to generate here, augmented machine code, or a virtual machine code which is not completely in scope with the syllabus, but I am just looking at the types of machine code. You have virtual instructions which can be run on any architecture with the virtual machine as interpreter, or a just in time compiler. Example is Java, basically write once run anywhere logic. So, here what happens is the compiler should basically be in a position to process source program. It prompts the error in the source program, and it should be in a position to recover or correct the errors, and it should produce assembly language program, and the assembler takes this assembly language program as input and converts that into a relocatable machine code. So, these are the jobs of a compiler basically, okay. And nowadays compilers comes with the assembler, and therefore, when you have a source program given as input, it is going to convert that into a final machine code consisting of ones and zeros. So, let us look at these two information. The time of conversion from source program into object program is called as the compile time, and the object program is executed at runtime. So, we are interested in compilation, but we should also have some knowledge about how memory is going to be allocated, how memory is going to be distributed during runtime when designing a compiler. So, interpreter is also a translator, so which is nothing but a language processor that executes the operation as specified in the source program. Typically inputs are supplied by the user, and it processes an internal form of the source program and data at the same time. Therefore, no object program is generated for an interpreter. So, how do I compare compiler and interpreter? One is a higher degree of machine independence and high portability, that is your compiler. It has other one is dynamic execution, modification or addition to user programs as execution proceeds, and dynamic data type is supported. The type of the object may change at runtime, and it is easier to write. So, there is no synthesis part which is required, and more source text information is basically available with the compiler. The machine language target program produced by a compiler is much faster than an interpreter at mapping inputs to outputs. So, this is one of the fundamental advantage of having a compiler. An interpreter on the other hand is better with error diagnostics as it executes the source program statement by statement. So, with these understanding, we will just try to get to the overview of the compiler. So, this is the compilation process as we already know. This is the interpretive process where you have a source program, you also have data here in the compile time itself, and then it produces the result. So, you can look at this compiler which is going to analyze the source program. The analysis part, that is, you have analysis part, you have what is called as a synthesis part, and you also have you could have group your compiler phases into front end and back end. So, first let us look at the analysis part. The analysis part tries to break the source program into constituent pieces, and it imposes a grammatical structure on them. It then uses this structure to create an intermediate representation of the source program. So, you can think of this as having two parts. The first one is the analysis part. The analysis part basically it is going to be language dependent, that is the source language dependent, and it is target independent, that is it need not care till this particular point what target machine code is it trying to look for. Okay. So, therefore, when you give it a source program, it is going to break this into small chunks, small pieces, and then analyze for its correctness, and after ensuring it is correct, it is trying to put them into a intermediate representation and give it to the next part of the compilation process. That part is called as the synthesis part, where given the intermediate representation as input, it is going to convert that into a final code depending upon the target machine. And in the process, what happens is a simple table is getting created. Okay, we will just go through that in the next few slides. The analysis part is often called as the front end of the compiler, and the synthesis part is called as the back end of the compiler. Okay. So, the front end is nothing but it is trying to break the input program into small pieces of chunks, and then based on these chunks it is going to verify whether the chunks are correctly organized for grammar, etc., and grammar and meaning basically, and then it is going to convert this into an intermediate representation. For at this till this particular point of time, it does not require what is called as the target machine need not be known till this particular point. After that, with this intermediate representation in place, it is going to convert this into a final machine code based upon the architecture of the machine it is targeting. The first few parts are called as the analysis part is called as the front end of the compiler, and the back end of the compiler basically does the process of synthesizing to generate machine code. The front end is language dependent and it depends on the source language, but it is target independent. On the other hand, the back end is going to be target dependent and depends on the target language, but it is going to be source independent. So, this is basically what happens. Source program, the analysis has got 3 phases, the synthesis has got basically 2 phases, and the tables are basically a symbol table and a error handler table, both are available here. So, in the analysis part you have lexical analysis, syntactic analysis and semantic analysis. Lexical analysis basically verifies whether the tokens are correct or incorrect. Syntactic analysis ensures that whether the tokens are arranged in a correct order or not. Semantic analysis tells you that whether the types of the tokens are correctly aligned or not. On the other hand, for the synthesis part, so this is going to be an intermediate representation. So, the edge here corresponds to intermediate representation that is given to the synthesis phase, where it generates target code and also optimizes the target code. So, if you look at the front end grouping, back end grouping, the analysis grouping based grouping and the synthesis based grouping. So, how many passes should a compiler go through? Can I map, I have here 3 parts in the analysis phase, the 2 parts in the synthesis side, and I have one more intermediate representation part, So, should I go for 6 passes, for one for each? That is going to be a lot of time. So, therefore, what we normally do is we will try to combine some phases into groups and call them as passes. So, the work done by a compiler is typically grouped into phases. Okay. So, this is what we talked about as the phases of the compiler: lexical phase, syntactic phase, semantic phase, intermediate code generation phase, code optimizers, and finally code generators. These 6 phases along with the symbol table and the error handler is going to convert your source program into target assembly language program. Then it is up to the assembler to convert that into machine language finally. So, what happens here is, let us go through it sequentially. The first phase is called as the tokenization phase, or it is called as a scanner. The lexical analyzer essentially reads the stream of characters from the source program and combines the character into meaningful sequences called as lexeme. Lexeme is nothing but a sequence of characters, and for every lexeme, the first phase of the compiler essentially produces a token of the form which is passed to the next phase of the compiler. So, this lexeme will have basically a token name, and then it is going to have an attribute value. For example, if I consider a statement like int a comma b, okay, a declaration called as int a comma b, here a is a lexeme and the token it gets is going to be called as an identifier. Identifier basically tells you it is a variable. Okay. So, that is one simple example. The token name is normally an abstract symbol which is used during syntax analysis. An attribute value is nothing but the points to entry in the symbol table for this token. Blanks will be discarded by the lexical analyzer. Okay. So, you have a token name and an attribute. The token name is nothing but the symbol used during syntax analysis, and an attribute is nothing but it points to an entry in the symbol table for this particular token. So, you are putting it in a symbol table, right. So, the symbol table ID or the symbol table address will basically be the attribute it gets. Now, after getting the first phase of the compiler, which is the lexical phase, which is going to simply scan through the tokens and then get the information about the token name and the attribute value. Now, I have a sequence of tokens after the first phase. Then now my job is to check whether the sequence, do they form a meaningful sentence or not. To be very precise, do they form a meaningful statement or not. That is what we are trying to check here. So, it is normally in practice that this lexical phase and syntactic phase go together in a single pass. So, what happens is we will see that when we move on to the subsequent chapters though. So, what happens actually is when the lexical phase will give a token to the syntax analysis phase, the syntax analysis phase basically takes this token, checks whether it can manipulate with this token. Okay. If it is not able to proceed further, it is going to ask another token from the lexical phase. So, it is going to issue a give token command, and the lexical phase will basically give a token. Okay. So, it issues a get token, lexical phase will basically give a token to the syntax phase. So, these two phases could basically be grouped into one pass. Okay. So, that is what we are going to look at it later. So, where the second phase essentially what it does is, it uses all the tokens given by the lexical phase and tries to form a syntax tree, otherwise called as the parse tree or the derivation tree. Okay. The parser uses the tokens produced by the lexer to create a tree like representation that verifies the grammatical structure of the sequence of tokens. Supposing if I have int a comma b semicolon, it is a valid statement, it is a valid sentence. Okay. If supposing if I give simply a comma b is not a valid statement. Okay. It requires the keyword int before a. Okay. So, it uses the tokens given by the lexer to check whether they form a sensible sentence or a sensible statement. So, this typical representation is a syntax tree in which each interior node represents an operation and the children of the node represent the arguments of the operation. The third phase is the semantic phase of the compiler, which is it uses the output of the parser, that is the syntax tree, and the information available in the symbol table to check for semantic consistency in the source program. Type checking basically happens in this phase. Okay. Type checking in the sense that it gathers type information and saves it in the symbol table or the syntax tree for subsequent use during code generation. For example, if I want to add two numbers, a is equal to b plus c. Okay. So, b should be if b is an integer and c is also an integer, then a gets the value as a can be an integer. Okay. Supposing b is a floating point number and c is also a floating point number, then a gets the value as a floating point number. On the other hand, if b is a floating point number and c is an integer, in that case what type will I assign it to a? That kind of a type checking basically happens here, and it is up to your design, it is your compiler. So, you can design it where you could put it as an integer, or you can say treat that as a floating point number, it is up to you. So, that kind of type checking basically happens here. This is what I just now said. Array index, one more thing is another few more examples are the array index need to be an integer. Okay. So, supposing if I say a of 100, so 100 is a integer, I am going to check whether this index subscript of an array is going to be an integer or not. If it is floating, it should be an error. So, I just throw an error here and I log the error in my error handler. Okay. So, whatever errors basically happens from the first phase till the last phase gets logged into the error handler basically. Okay. And you also do what is called as coercions, which is an explicit type conversion. Okay. Which is an explicit type conversion in the sense that supposing if I give 60, okay, or if I say a into 60, and supposing a is going to be of type float. So, what I am doing is I will convert this 60 into 60.0. So, I will do a into 60.0. So, this is what basically happens as type conversion, which is called as coercion. A binary arithmetic operator may be applied to either a pair of integers or to a pair of floating point numbers. If the operator is applied to a floating point number and an integer, the compiler may convert or coerce the integer into a floating point number. So, this is what is called as coercion, which is implicit type conversion. And in the fourth phase, the compilers generate an explicit low level or machine like representation of the source program. This intermediate representation should be easy to produce and it should be closer to the target language. Okay. So, this is what is the primary requisite for this particular phase. So, what is its input? Its input is going to be a syntax tree from the third phase of the compiler, and the output will be an intermediate representation which is going to be closer to the target code than to the source code. One example is 3 address code is one type of an intermediate code. Okay. So, where it can have at most 3 operands and 2 operators. Out of the 2 operators, one has to be an equal to assignment operator. So, examples are x is equal to y operator z, x is equal to operator y. So, here this is one type of a 3 address code. So, y, z, x are the 3 addresses here, and this is one operator here, and I have an equal to operator also. After intermediate code generation, we can actually go in for what is called as code optimization. You normally try to do an optimization at the intermediate code level itself, or you can try to optimize at the final code level. If you try to optimize at the intermediate code level, what happens is this will result in faster, shorter code, and it is going to consume less power for the code generation phase, and simple optimizations can basically be applied here itself. Therefore, your code generation complexity also gets reduced, its time also is going to get reduced if I try to optimize in the intermediate code level itself. And the last phase of the compiler is your code generation phase, where if the target language is machine code, then registers or memory locations are selected for each of the variables used by the program. Then the intermediate instructions are translated into sequences of machine instructions to complete an operation. So, the consideration here are the assignment of registers to hold the variables and the choice of instructions involving registers and memory or a mix of the two is also going to be another consideration. So, should I put everything into the registers, or should I basically try to put some in registers and some in memory and then try to do an operation? That is going to be a point of consideration here. Now, we talked about what is called as a symbol table in the phases of the compiler. The symbol table is a hash table like data structure. containing a record for each variable name with fields for the attributes of the name. The data structure is designed to help the compiler identify and fetch the record for each name very quickly. It is also to store or retrieve data from the record very quickly. So, it is basically managed as a hash table, which effectively retrieves, stores and accesses data at a very faster rate. It also interacts with all the compiler's phases. The attributes may provide information about the storage allocated for a name, its type, its scope. Function or procedure names, such things as numbers and types of its arguments, the method of passing each argument and the return type is also available in the symbol table. As I already talked about, so these are the phases of the compiler, and every time it is going to interact with the symbol table. Every phase will interact with the symbol table. So, as I proceed for the next few modules, we will talk about how each each phases tries to act the symbol table will be basically discussed. Here we talked about passes against phases. So, several phases can be implemented as a single pass consisting of reading an input file and writing an output file. So, as I already said that it is a multiple pass compiler, where the first pass will basically be pre-processing and macro expansion. The second pass will be the syntax directed translation and intermediate code representation. The third pass is optimization, and the last pass is going to be code generation. So, what happens here is the first pass is pre-processing and macro expansion. So, the remaining, the analysis phase basically happens in one single pass, that is verifying whether a particular token is correct or incorrect, whether a sequence of tokens is going to make meaningful statements, and then I will also do type checking there and then convert into a syntax tree representation and then generate intermediate code for the same. Intermediate code is what we talked about as 3 address code there. So, from the lexical phase till the 3 address code, it is going to be one single pass, and then optimization is going to take another pass, and finally code generation is going to take the last pass. This is just one way. So, you can basically try to do it in another way also, where we looked at the examples earlier. And one more thing which I wanted to talk about here is when we looked at the error handler, the error handler basically is going to interact again with all the phases of the compiler, where the error handler, whatever errors you encounter will be logged into the error handler from every phase, and then it allows the compiler to continue with its remaining compilation process, and then finally when it lands up in a problem, it can recover from the errors based by looking into the error handler, and the error handler will basically be prompted to the user for correction by the user for proceeding with for the next for subsequent compilation iterations. So, to summarize this, basically we have seen the phases of the compiler, where we looked at 6 phases: lexical, syntax, semantics, intermediate code generation, and finally code optimization. We also talked about the need for an error handler and the symbol table, and we also talked about translators here, where we looked at interpreter and translator as 2 inputs. So, with that we have seen the phase of the compiler. Now, we will take an example and discuss that in the next module.